Okay, so this is a little practice for your pre-lab assignment on the Diels Alder. We're going to analyze EE24-hexadiene 1-ol, which is one of the starting materials. I'm going to analyze it for you here. I'm going to do the same stuff to this that you're doing for the pre-lab, for the product, okay? So this is to help you figure out what you're doing. You are asked to analyze your product, and I'm going to analyze this starting material in the same way. What we're going to do is we're going to put the expected integration, we're going to predict the chemical shift, and then we're going to predict the multiplicity. This will be done in the experiment. The actual experimental chemical shift and the observed multiplicity will be done in the analysis too, so after the experiment. All right, so here's what we're going to do. We're going to start filling in this table, and we're using this table of chemical shifts to give us some idea of where we should be able to find these different protons. Okay, so let's look at A first. A is the methyl. What integration should I expect for that? Well, there's 3 hydrogens and they're all equivalent, so it should be 3. Predicted chemical shift. Let's look at this. These hydrogens are on a carbon that's next door to a double bond. So that's allylic. So it's this one right here. So we should expect to see that at around 1.8. What is the multiplicity that we're expecting to see? These 3 carbons are on a carbon that's next door to a carbon with 1 hydrogen. So we should see a doublet. Okay, let's do B, same way. We've got B here, which is 1H, and it's a vinylic hydrogen. So it's right here, 5 to 5.3. It's next door to a carbon with 3, and it's next door to a carbon with 1. So we use the n+1 rule. So that should be a quartet. And this doublet, this single hydrogen would split it into a doublet. So we should have a doublet of quartets. All right, let's do C. C is 1 hydrogen. It's vinylic, so 5 to 5.3. And it's next to this, it's on a carbon that's next to a carbon with 1 hydrogen, and it's on a carbon that's next to a carbon with 1 hydrogen. So we should see a doublet of doublets. D, another vinylic, 1 hydrogen, 5 to 5.3, and it's next to a carbon with 1 hydrogen and next to a carbon with 1 hydrogen. So we should see doublet of doublets. And then E, again, 1 hydrogen, 5 to 5.3, it's vinylic. And it's next door to 1 hydrogen, and it's next door to 2 hydrogens. So it should be a doublet of triplets. F, okay, F is 2 hydrogens. And those hydrogens, they're methylenes, and they're next door, oh no, they're on a carbon that has an oxygen. So they're alpha to an oxygen, so that makes them somewhere around 3.8. And they're also allylic, so it's like 1.82. So it's just going to be greater than 3.8 is what that tells us. The fact that they are allylic, they're next door to a carbon that's on a double bond, and they're also have an oxygen, makes them further downfield. All right, so they will be split in 2 by E, and maybe split in 2 by H. Sometimes that happens, so maybe a doublet of doublets. We'll see. Or it could be just a doublet. Sometimes the hydrogen on the oxygen doesn't cause splitting. We'll wait and see. All right, G is 1 hydrogen, and G, let's see, where should that be? Let's find it in the table. OH is anywhere between 0.5 and 5, so we don't know where that's going to be, and it can either be a singlet or a triplet, depending on if these F hydrogens are splitting it. Okay, so that is what you do for your product on the pre-lab. All right, you're going to do that. This is the starting material. I'm just doing this as an example. Let's do the carbon the same way. We're going to look at the carbons and assign chemical shifts. Okay, remember carbon is just chemical shift. There's no integration or multiplicity with carbons. So all we can do is do the chemical shifts. So let's look at A. It's a methyl. So where do we have that? If it's just a methyl, it's somewhere between 10 and 30. B is a vinylic carbon. So it's an alkenyl. So 100 to 150. These are pretty broad ranges, right? C is going to be 100 to 150. D, 100 to 150. E, 100 to 150. And then F is a methylene. So it could be 15 to 55. Oh, but it's got an oxygen on it. If it's attached to an oxygen, that makes it 40 to 80. So something like that. Okay, so we're going to use HMQC to assign these, which is a really nifty tool. It relates the proton NMR, once we assign all of those, to the carbon peaks, all right? So it works really well. So that's the plan with that. Okay, I wanted to just show you, there's something kind of confusing in the pre-lab. I'm afraid my wording is going to confuse you, and I want you to understand. What I'm going to ask you to do is to try to assign the peaks in your product, not in this, in the product. But I'm going to show you that it's really hard to do that because all of these are kind of like the ones in the product. They're all very similar. But if you look, so this integrates as 1. This is 1, 1, 1. So this little group of peaks is 1 signal. This is 1 signal. And this blob is actually, if we expand it, you can see there's 2 signals there. All right, this is integrating as 2. That's interesting. This integrates as 1. This right here is water. It's a water peak that's in our acetone solvent, and this is our acetone. That's our solvent peak, okay? So we ignore those. And then you look at this, it says 3.52. Hey, ding, ding, ding. It's off a little bit on its integration, and I can tell you reasons for that, but we're going to go, that's 3. So it's pretty easy to look at our table and figure out what that one is. Stop and think. What is the only one that integrates to 3? Oh, it's that one. Yeah. So let me look. It's 1.69 is its chemical shift. So we're going to write in the actual chemical shift, we're going to put it in here, 1.69. All right, and that's pretty close to what we predicted, 1.8 and 1.69. So when it says actual chemical shift, we're going to do that week 2, except for 1 peak. That's what I want you to do. I want you to look at the NMR and see that there is 1 peak that you can definitely assign from your predictions, and it would probably be due to the integration. Hint, hint, hint. Okay, and then for this one, we could also maybe go ahead and assign F, the one with 2 hydrogens, because this signal right here integrates to 2. So let's get that chemical shift, and it is at 4.03. 4.03. So I can go ahead and get those, and those are the 2 that I can get. On yours, you're going to be able to get 1, all right? And because all of the others are just 1 peak, and you're not really sure which ones are which. Okay,